Alright, so welcome to the fourth and final video for the heat transfer homework series. Last time we did a von Neumann analysis to demonstrate an instability in R. This time we're going to do what's called a Crank-Nicolson method, and this is going to give us a lot more versatility in the R we can use for our analysis, and we'll demonstrate at the end when we go to code what we find up here. But first, let's go back to our our original problem, in which we said that we can model the situation we're working with this simplified form of the heat diffusion equation, which we then expressed thusly. So Tj to the n at some time n plus 1 minus Tj to the n equals this alpha delta x squared, which we called r previously, and then times everything here in the parentheses, Tj plus 1 to the n minus 2 Tj to the n plus Tj to the n minus 1. All right, so this position at some position to the left and to the right. This is supposed to be Tj minus 1 here. Tj minus 1 and not n minus 1. So it's all at the same time here, but it's at a position to the left and to the right of this Tj. So what we want to do here is go ahead and express this side in terms of the current time step plus the previous time step over 2. And what we're doing there is basically finding the slope of this point plus the next point and dividing by 2, which will allow us to sort of find the slope, which is what the derivative is going to be doing. So I'll show you what we're going to do here. So like I said, we're going to keep this side the same here for right now. Tj n plus 1 minus Tj to the n. So our temperature at position J at different times there equals alpha delta T over, and we're going to divide it by 2 here, delta x squared. We're dividing it by 2 because we're going to divide what is in the parentheses by 2. I'm just factoring out now. So what we wanted to do is do at some time step n plus 1. We'll call that current, even though it's n plus 1. We'll just call it current so that we can call it Tj to the n, our previous time step, previous in terms of relative position to n plus 1. All right, so Tj to the n, Tj plus 1 to the Tj, or Tj plus 1 to the Tn plus 1 minus, all right, 2 Tj to the n plus 1 time plus Tj minus 1 to the n plus 1 time. And what we're going to do is add the previous to that, which would just be n, and divide by 2. Like I said, we already did that too, factored it out. So that would just be this right here. This right here. It's all in terms of n, so I'll just copy that now. Tn j plus 1 minus 2 Tj n plus T to the j minus 1 to the n. All right. And so that is what we're going to do to start the Crank-Nicolson method. Next, we're going to isolate our terms, and I'll show you how we isolate those next. And so what we're going to do here is, now that we've expressed this in the way that we like, we're going to try to isolate, or rather separate our previous time step from our current time step onto different sides of this equation. So we're just going to do a little bit of algebra. And to make that a little bit easier, we're just going to call this term here R. I'm just going to call this R. And we do notice it is a factor of 2 less than the one we did for our previous finite differencing. For the von Neumann analysis, it is going to be 2 less, but that's okay. We're just going to call it R and make this a little bit simpler here. So let's go ahead and try to put our like terms on one side here. So this will be Tj to the n plus 1 minus Tj to the n equals R times Tj plus 1 to the n plus 1 minus 2 Tj minus, rather, minus 2R actually, minus 2R, Tj, temperature J at some position J is plus 1, plus R, T, temperature plus 1, and then once again, just multiplying each of these by R here, plus R, Tj plus 1. minus 2r tj to the n plus r tj minus 1. Alright, so multiply all of our terms by r there. So multiply each of our terms by r. Let's go ahead and put our n plus 1s on the left side. So the tj n plus 1 minus r t to the j plus 1 plus 1 any other plus 1s. So we'll do plus 2 r t to the j n plus 1 plus 2r, and then minus r tj minus 1. Make sure the left is the times the minus 1. Alright, so that's all of our n plus 1 terms on one side. Let's move this term over. This is our tj to the n. Alright. Plus r tj plus 1 the n minus 2r tj the n plus r tj minus 1 the n. Alright, let's see if we can simplify this a little bit further. So I see this is supposed to be plus 1. So I see a tj n plus 1, tj n plus 1. So let's just go ahead and call this, let's call this 1 plus 2r times tj to the n plus 1 minus rt j plus 1 n plus 1 minus r tj minus 1 plus 1. Alright, that's a little bit simpler. Can we do the same thing over here? I see a tj to n, I see tj to the n, so that would be, I'm sorry, this is supposed to be plus 2 actually. I'm looking at it. This is, yeah, because we're adding this to this, this should be plus 2. Right? And over here, we're subtracting it, so this would be 1 minus 2r. Oops. 1 minus 2r rtj to the n this time. So multiply by that quantity. So we took care of those two. Plus r tj plus 1 n plus r tj minus 1. To the n temperatures to the left and to the right. All right. Okay, so that's our equation here, and notice that this depends on the temperature. It depends on a lot of unknowns with our temperature. The next time steps, we have all these things. So it's a little bit more complicated of an equation than we've been working with before. So to solve this, we're going to do a little bit of matrix math. Put this in a matrix and then solve it and demonstrate the stability of R in Python. But first, let's see how we can put this into a matrix and then what we'll do from there. So what we want to do now is we want to take this equation here and we want to express in matrix form. We want to express this as a set of equations in matrix form so that we can solve for some things. So this is going to be our TJ right here. This is going to be our TJ column. And let's elaborate on our boundary conditions real quick. Inside here, we'll have our t at j equals 1, 2, all the way down to tj equals 98. And that's because on the boundaries, we'll have at tj equals, at j equals 99, and at t at j equals 0, we'll have our boundary conditions, one at 350, the other at 400. And that's just from the problem. We remember that those are the boundary conditions. We're raising up the temperature at the sides of these bars to 350 and to 400. So on this diagonal for this matrix, we're going to have 1 plus 2r multiplied by our tj, and then minus r is modifying our terms on both sides, at the right and the left. So you'll see 1 plus 2r is just going to go down this diagonal, and each time we're just multiplying each of our tj plus 1, our tj minus 1. Both are minus r, so we don't really have to worry about a lot there. Both are minus r, and we see what we see is that we're not using this whole matrix. In fact, we're only using a specific part of it, minus r. And so as you go across, you see we're just using the diagonal of this whole matrix here. And that's going to be helpful for when we go to coding. So now I'm going to show you, we're multiplying this by this, and that's going to equal what we get over here is just going to be, I'll elaborate on that in this next here. I'll go to that part next. Yeah, so what we get when we multiply these together is, looking at our equation down here, the temperature, the temperature to the right, well, that's just going to be, excuse me, our R at T for J equals 2, all right, plus, now let's do at the temperature in the middle, which is just going to be, remember, our 1 plus 2R, our 1 minus 2R, our 1 minus 2R, 1 minus 2R, and some T J for the first one would be equals 1. And then, of course, now to the left, we have plus R at T 1 minus 1 would just be 0. And also, we're not quite done because we notice there's no, on the first term, we have no negative R. Looking at this, we notice we have to actually add by R at T equals 0, or T for, if you want, J of 0, and plus R for T at J equals 99. And that's for our first and our last part of this matrix, we have to add by this and this, because this term here is going to come from our 1 to the left, and this term here is going to be our 1 to the right that we're actually going to be adding. There's no minus R. We got to add these. We know what they are, 400 and 350, and so we got to factor that in. But that's just for the first and last one. Overall, I'll show you what, and the next one would be, for example, where we don't have to do that. That would be R T at J equals 3 plus 1 minus 2R T at J equals 2 plus R at T J equals 1. Right, and so we're just going to go on and on and on until we get to our last TJ, and that's how we express it using matrices. It's going to be a lot easier this way. This set of equations in matrix form is going to be a lot easier for us to code, and actually going to allow us to be able to plot this temperature evolution into the bar, where our R value is not going to be limited by anything significantly. So we'll get to that coding part now. All right, so stepping back here into our code, we're trying to demonstrate stability above 0.5, so let's use an R of 1 for this time. And let's go ahead and set up our array for our initial temperature again. So that's going to be T equals np.full. The number of little slices we have, we'll do nx for the number of slices, and we're saying that those are all starting at 300 Kelvin. 300 Kelvin. All right, and let's go ahead and do our boundary conditions. So that's our T of, that'd be 0. We said one side is going to be 350 Kelvin. We'll make that a float. Oops, not that. I want it to be floating. And the T of -1, the one at the other end that is going to be 400. Oops. It's going to be 400 Kelvin. All right, so this is our initial matrix we're working with here. Next, let's move on to the stuff we just did on the whiteboard. Okay, so let's go ahead and put in that first matrix that we found on the board. All right, that's A equals NP dot zeros. And we had 3 diagonals, and that's going to be NX minus 2. Why minus 2? Because, once again, we have 2 boundary conditions, so we're not going to include that as a part of this. That might need to be in parentheses, I don't remember. We'll go ahead and do that. And so let's define our first diagonal here. A1 to the end there. So that is what we just said. That was just going to be -r. That was our top diagonal. Not range, -r. Our second diagonal, actually, once again, this is Python, so this should be 0. Shouldn't it? That should be 0 because of indexing. Our second diagonal, we said was going to be, that was just going to be 1 plus 2r. 1 plus 2 times r. 2 times r. And our third diagonal, we just said that would be also -r. That's our bottom. So our top is -r, 1 plus 2r was the middle one, and -r was the one below it too. So those A0, A2 are the same there. I think that we need commas there. All right, so we just put in our A's. Let's put in the next part now. All right, so let's go on to our next matrix. This is going to be B. We'll call it B equals NP dot zeros. Once again, this will be NX minus 2. We're dealing with everything there in the boundaries. NX minus 2. And now is where we'll write our equation for B. So here I have the matrices that we just wrote out on the board. And we're going to be putting this into it. So it's going to be our R times our temperature to the right. R times temperature to the right. T right 2, and it's going to be plus 1 minus 2r times T1. Our temperature in between our boundaries here from 1 to -1. Everything in between. Plus now, and is that one multiplied? Yes. This one will also be multiplied just by R, T, and this time everything to the left there. -2. This is 2. This is -2. The right and the left, and then the one in the middle. So that's plus R, and there should be times sign there. Times. So yeah. So this is that equation, and we're going to iterate that over and over, but that will update that value there. Now let's go ahead and put our boundaries in for that. Okay, so we remember here also we had our boundary conditions here where we had R multiplied by our boundary T0 and our R multiplied by our boundary T99. Right? So let's go ahead and specify that. R at 0 and R 1 at -1. The one at 0 is going to be equal to 0, 0 plus R times RT at 0, right? r times our t at 0, and this b at 0 will update. And likewise, it will be the same with our other boundary condition, now at the other end of it. Not a capital B, a lowercase, -1 plus r times t at -1, our other side of the bar. So this is for the left side here. This will be for our right side of the bar. And those are our boundaries there on B. All right, let's go ahead and now iterate this in a for loop so that we will actually be able to update a graph like this. All right, so let's actually go ahead and first tell this to chart this, to graph this. So that's going to be fig2 equals make subplots. All right, fig2 dot add scatter, and we'll have x equals our x again, our y is going to equal to our temperature, and we'll just name it, I don't know, call it the same thing, t profile. All right, now we're going to go ahead and put a for loop in to iterate this function here. All right, so let's move on to our for loop. So for I in range, let's say we'll do it 3,000 times there. And I in range 3,000. I'll have some function. Oops, we'll get to our t here. But let's also just talk about how many times we can do it. Let's update our graph. Let's do it every 100 times. If I, where's the percent here? Of 100 and then 0. So we'll update it every 100 times there. And then we will add. We'll add it. We'll add fig2 this time, which is going to be, just going to reuse this code here, but this time for fig2. Fig2. And yeah, we went ahead and did every 1,000 this time. But this, for the previous one, we're going to do every 100 this time. And I think that'll be fine. I think that should be enough. And yeah, so let's go ahead and do the t that we're going to do. Also, one thing I'm going to do is from scipy import linear algebra, or was it? You know, I'm actually going to check on this. We got to import. Basically, we're going to import a function to solve a banded matrix. So I'm going to check on that to make sure this is right. But I think it's import solve banded. And maybe it wasn't scipy. Maybe it was lin algebra. We'll check on that, and then we'll get back and code our t, our banded matrix there. All right, so it was from scipy dot lin algebra. Scipy dot lin algebra. We're going to import this solve banded here, and that'll allow us to solve for our banded matrix. You know, I don't think we need this. Okay, we can get rid of that part here. All right, and now we're going to put our banded matrix. We're going to put all our t's, and we're going to put this into our for loop so that it will update our graph. So let's go ahead and do that now. Okay, so here we're just going to put in our banded matrix here. So for t, at the everything in the boundaries there, from 1 to -1. Everything in our boundaries. We're going to do our solve banded function that we that we imported there, and that's for our A and our B 1 there. So our A and our B that we just defined. No, not bin. Our A and our B. And we want to update our B again using this code here that we just described, but we wanted to update for every iteration. Let's make sure that's all properly aligned there. Yeah. So yeah, for our range there, we wanted to solve this band matrix, update it every 100, update our B value, and we'll see if we have any constraints on this R this time. So we'll go ahead and do that now. All right, so let's go ahead and run this, see if it works. We'll just run them all here. Okay. Oh, so this 2 here, this should be on the other side, and we copied it, so this is 2 to the end there. So we had it on the wrong side of that colon there. And also, this should have parentheses there. All right, let's try that one more time here, see if it works. All right, so it doesn't like this. Oh, it looks like, yeah, it looks like we didn't put a multiplication sign there next to our R. And once again, I bet we didn't do it there because we just copied it. Yep, we got to multiply it with the little asterisk. All right, let's try this. 3rd time's a charm. Can't interpret 98 as data type. Yeah. Does this need to be? I'm gonna take a look at this and I'll be right back. All right, so I think we found the error here. There's a misplaced parenthesis in that equation, which was messing it up. Also, importantly, this was an integer, and this needs to be float too. If it doesn't do that, we're not going to have the right shape at all. So those are 2 errors that needed to be fixed right there. Let's go ahead and run it this time and see what happens. All right, so this is the first one, and this is the Crank-Nicolson one. Perfect. All right, so that is awesome. This now, what's significant about this is this was for an R of 1. Yeah, we had an R here, but this was for 0.1. But this was for an R of 1, which is great. So we can also, if we zoom in up here, it looks pretty good. Let's try it for a bigger R now, see what happens. True an R of like, say 5. And then we'll run all again here and see what we get. All right, so this we do see a bit of an inaccuracy. It's not an instability, but it is an inaccuracy where it does spike up too much there. And that's because our R is too big, and if our R is too big, then our delta X was too big. So because we're doing a differential when our slice is too big, it's going to be inaccurate because we have we're going over too far a distance for it to be accurate. But even though that is inaccurate, it still does come to a nice profile. It doesn't go to negative infinity. Eventually, we do get what we're looking for. That's just something to keep in mind. That's one limitation of this Crank-Nicolson. So if your R is too big, then that delta X will be too large an area for this function to be accurate over. But for a value of 1 for our R, you can't really see too much there at all, and this is just a great distribution we got here. So I think that's it. Yeah. So we just worked through our Crank-Nicolson method and showed that it does have stability. We'll show one more just in case. We'll do it for 4 as well. Just so we have three examples. Now we have not proving it, but we're demonstrating that this is certainly stable. Yep, looks good there. And though there are inaccuracies, it's not an instability. And so that's what makes this Crank-Nicolson method a lot more powerful than the von Neumann analysis that we just did. With the finite differencing, we showed that the R had to be less than 1/2 there. So this Crank-Nicolson method is really powerful. We went and showed how to do it with some matrix math there and coded that into this. And luckily, Python is able to do all these iterations for these matrices a lot quicker than I could. And I think that's it. We have a pretty stable little temperature evolution there in our plot. So thank you very much. I hope you enjoyed these lecture homeworks. And that is all. Thank you. I'll see you next time.